Hey everyone, and welcome. Today, we're diving into something we see every single moment of our lives. Motion. From a ball rolling across the floor to planets spinning around the sun. And what's wild is that it's all run by just a handful of simple rules. To get to them, though, we have to start with a surprisingly simple question. Right? This is it. It sounds like a question a kid would ask, but honestly, it stumped the smartest people on Earth for thousands of years. Think about it. If you push something, why does it always eventually just stop? What's really going on there? So, for the first part of our story, we've got to go way back, like over 2,000 years ago to ancient Greece. For centuries, the answer to that question seemed totally obvious. It was just common sense. But as we're about to see, that common sense idea sent science down the completely wrong track for a very, very long time. So, the brilliant thinker Aristotle, he looked around at the world and saw what we all see, right? To keep a cart rolling, you got to keep pushing it. To keep an arrow flying, well, he figured the air must be swirling around behind it, pushing it along. And you know what? It feels right. It's intuitive. And because it felt so right, for the next 2,000 years, that was basically accepted as fact. This was the law of the land. But here's the twist. As natural as it feels, this core idea about how our universe works is completely, totally wrong. So what's the deal? Where's the mistake in his logic? Well, it turns out Aristotle, and pretty much everyone after him for centuries, totally missed a key player in the game, a kind of invisible force that is always, always working against motion. And that sneaky force is friction. It's the scuffing between the cart's wheels and the road that grinds it to a halt. It's the air resistance that slows down that arrow. Friction was the missing piece of the puzzle that fooled all of humanity for ages. So, to finally see the truth, it took a totally new way of looking at the problem. And this brings us to the next hero of our story, the genius, Galileo. He figured out that to understand motion in the real world, you first had to imagine a perfect world that couldn't possibly exist. Galileo used pure imagination. It's brilliant. He thought, okay, a ball speeds up when it rolls down a ramp. It slows down when it rolls up one. So what if the surface was perfectly flat? And what if it was perfectly, impossibly smooth, with no friction at all? Well, logically, it wouldn't speed up or slow down. It would just keep going. Forever. And just like that, with a simple thought experiment, he stumbled upon a revolutionary new idea, inertia. It's this built-in property of everything. It's a resistance to change. Objects don't want to stop and they don't want to start. They just want to keep on doing whatever they're already doing. So Galileo laid all this incredible groundwork. He gave us inertia. But it was Isaac Newton who came along, took this game-changing idea, polished it, and used it to build the entire foundation of modern physics with his 3 simple, unbelievably powerful laws of motion. Newton made it official with his first law of motion. All it's really saying is that an object sitting still is going to stay still, and an object that's moving is going to keep moving at the same speed and in the same direction forever, unless some outside force comes along and messes with it. Now, this is the crucial insight. This is the part that feels so weird but is absolutely true. To the universe, sitting perfectly still and moving at a steady speed are basically the same thing. They're both balanced states. The total force on them is 0. You don't need a force to keep something moving. You only need a force to change its motion. You've totally felt this before. Picture it. You're on a bus and it slams on the brakes. The bus stops. Your feet, thanks to friction with the floor, stop with it. But the rest of your body? Thanks to inertia, it wants to keep right on moving forward. That lurch you feel? That's it. That is you, personally, experiencing Newton's first law. Okay, so law number 1 tells us what happens when forces are balanced or when there's no net force at all. But what happens when a force is applied? And where do these forces even come from? Well, that's where Newton's next 2 laws come in. Here it is. Maybe the most famous equation in all of physics, F equals ma. The second law gives us the math. It tells us exactly how much an object's motion is going to change. The bigger the force, the bigger the change. And the heavier the object, the more mass it has, the harder it is to change its motion. I mean, this is why it's way harder to get a huge truck moving than a little tiny car, right? The truck has so much more mass, so to get it to accelerate at the same rate as the car, you need to apply a way bigger force. It's just F equals ma in action. Simple, elegant, and it explains so much about our world.
And that brings us to the third law. And this one is just beautiful. It tells us something really deep about the universe. Forces never act alone. They're always part of a pair, an interaction between two different things.
And this law perfectly solves a classic puzzle. In the total emptiness of space, there's no air, there's nothing to push off of. So how in the world does a rocket move? Well, here's the first part of the force pair, the action. The rocket's engine fires, and it pushes hot gas out the back with a tremendous amount of force. It's literally throwing its own fuel backward. And for every action, there's an equal and opposite reaction. As the rocket pushes the gas backward, the gas pushes the rocket forward with the exact same amount of force. The rocket isn't pushing on space, it's pushing on its own exhaust. It's incredible. So let's recap. We've got 3 laws. The first one tells us what happens when there's no force. The second tells us what happens when there is a force. And the third tells us that forces always come in pairs. Now let's put it all together and see them running the show everywhere. I mean, think about it. Every time you take a step, your foot pushes back on the earth, and the earth's friction pushes you forward. That's the third law. When you catch a speeding baseball, your hand has to apply a huge force to change its motion to 0. That's the second law. The gravity holding planets in their orbits, the force that keeps your car from flying off the road when you take a turn. It's all Newton. All of it. And that's what's so amazing. We have all these different names for forces, right? We talk about tension in a rope or the push from a spring or gravity from a planet. But underneath it all, they're all just pushes and pulls. And every single one of them has to play by these same 3 fundamental rules. So we went from an obvious idea that was dead wrong all the way to Newton's elegant equations that cracked the code for how everything moves. It really leaves you with a final, kind of amazing thought. If something as chaotic and complex as motion can be boiled down to 3 simple laws, what other parts of our complicated universe are just waiting for us to discover their beautiful simplicity?